Hi, this is Group Q, consisting of Jaden, Ramis, Joel, and myself, Farah. We will be analyzing the force vectors on a vertical lift drawbridge. A drawbridge is a type of bridge that has the ability to move its parts. A drawbridge can lift, slide, or rotate to accommodate for easy passing of boating traffic through a body of water. These bridges have existed for thousands of years and can be traced back to forts to control who entered. The older designs were hinged on one side and pulled up with chains. The modern designs of bridges came about due to the Industrial Revolution, which transformed the way these bridges were created, because steel beams were being mass-produced and distributed, which made construction easier and the bridges lighter, stronger, and more durable. The operation of these modern bridges therefore facilitated the development of new lift mechanisms. The drawbridge we will be looking at is the vertical lift drawbridge. This is a bridge whereby the middle of the bridge lifts while remaining in a horizontal position where the movable deck is attached to heavy counterweights and steel cables in 2 or 4 towers on the end of the bridge. A drawbridge is a prime example of many key engineering mechanics principles such as trusses, pulley systems, kinetics, and force vectors, of which we'll be focusing on the force vectors acting on the bridge when it is being lifted.
Now we'll be moving on to the topic behind these bridges, which is force vectors. Force vectors are a mathematical representation of forces, showing both the magnitude, which is the strength, and the direction of the force acting on an object. Forces are vector quantities, meaning that they have both magnitude and direction, and this vector representation is key to understanding how forces interact and how objects move under their influence. We can break it down into the main aspects, which include magnitude, direction, representation, and addition. First, we'll start with the magnitude, which represents the strength of the force and is typically measured in units like newtons, which is the SI unit. It is the length of the vector in a graphical representation. Second, the direction. The direction of a force vector shows the way that the force is applied. It's represented by an angle or by indicating the vector's orientation relative to a coordinate system, such as the x and y axes on a Cartesian plane. For example, if a force is acting to the right, the vector will point to the right along with the x-axis. If the force is acting upwards, the vector will point upwards along the y-axis. The third is representation, which comes in 2 different forms. The first is arrow representation. This is seen as a single arrow, where the length of the arrow represents the magnitude of the force, and the direction the arrow points indicates the direction of the force. Next is component form. This is when a vector is broken down into components along the axes, x and y in 2D or x, y, and z in 3D. For example, when resolving a vector f acting at an angle theta from the horizontal, it is separated into the horizontal x component and the vertical y component, typically using trig functions like sine and cosine. Finally, there is vector addition. When multiple forces act on an object, the net force or the resultant force is found by adding the vectors together. This is done by adding their respective components in the x, y, or sometimes z directions. In a pulley system, there are forces in the rope and forces on the object being lifted. When a force F is applied to the rope, which is typically at one end, it acts as a tension force in the rope, denoted by the letter T. It is generally assumed to be constant along the entire length of the rope. This is assuming an ideal massless rope and frictionless pulleys. The object being lifted experiences a downward force due to gravity, which is the weight of the object. This can be represented in the formula W equals mg, where W is the weight of the object, m is the mass of the object, and g is the acceleration due to gravity. To lift this object, an upward force via the tension in the rope must counteract the weight.
I'll be discussing the mechanics of a vertical lift drawbridge. There are 3 types of vertical lift bridges, which are readily identifiable. 2 by the method of operation, which is the tower drive and the span drive, and 1 by an overhead connecting structure between towers. This is called the connecting tower type. On the tower drive vertical lifts, the machinery is mounted on top of each tower. A large sheave is mounted on each side of the tower with counterweight ropes wrapping 180 degrees around the sheaves. One end of the rope is attached to the span and the other to the counterweight. As the drive machinery turns the sheaves in one direction, the cable raises the span and lowers the counterweights. When the rotation of the sheaves is reversed, the span is lowered and the counterweights are raised.
So to better grasp the mechanics of the vertical lift bridge, let's look at an example. Let's say we have a vertical lift bridge in static equilibrium that has a span that weighs 30,000 newtons. It's supported by 2 cables, each cable being attached to a counterweight. Say we wanted to find the tension values in each cable. The bridge span is evenly supported by the 2 cables and the system is in static equilibrium. This means that the total tension must balance the weight of the bridge deck. So we can write this as T1 plus T2 equals W and solve accordingly. Since the load is symmetrical, we will say that both T1 and T2 equals 15,000 newtons. Therefore, the tension in the cables are 15,000 newtons each. So let's take a look at the bridge now while it's in motion. In this scenario, we're looking at the same bridge except it's being lifted upwards at an acceleration of 1.5 meters per second squared. So before we get into tensions, we need to find the net force, which is found by using Newton's second law, F equals ma. To find the mass, we simply have to plug our given values into the equation m equals w over g, where m is mass, w is the weight, and g is the acceleration due to gravity. When we solve this, we should get the answer 3,061.2 kilograms. With this information, we can take the mass and plug it into Newton's law, giving us the answer of approximately 4,591.8 newtons. With this answer, we can calculate the total tension of the cables by adding the total weight to the net force. After working this out, we will get an answer where the total tension is equal to approximately 34,591.8 newtons. Since the tension is evenly distributed between the 2 cables, we simply divide our answer by 2, giving us that in each cable there is a tension of 17,296 newtons while accelerating upwards.